Hello, welcome to my lecture on magnetostatics. This is a lecture for my SEM 2 students, and we would be talking today about the magnetic properties of matter. So before we go into the magnetic properties of matter, let us recapitulate what we learned in our previous lecture. It was all about a force acting on a magnetic dipole or a current carrying loop, because a magnetic dipole is equivalent to a current carrying loop. Let us assume that we have a magnet over here. The north pole is over here and the south pole is here, and there are magnetic fields emanating from this magnet, and we have a current carrying loop here. Current carrying loop. Now this loop has B along this and current along this, so there would be a force. Sorry, because force is nothing but I of dl cross B. So dl along the tangent to the loop, B something at making an angle, and dl and B both are perpendicular and they are making a resultant which is along this. Similarly, at the diametrically opposite point, again the B would be along this, the current would be along this, and then the force would be along this. So the component which is perpendicular or parallel to the plane of the loop would cancel out because they are equal and opposite, and there would be a net force of attraction of this particular loop towards the magnet. That is what all actually happens when you talk about the magnetic properties of matter. In matter, you have small current loops like this, which are actually made up of electron current loops, which give rise to the phenomena of diamagnetism, or the spin of the electrons, which give rise to the phenomena of paramagnetism. And since all matter contains atoms and electrons revolving around certain orbits, we have magnetic property to be there in all the materials. That's why we are going to study today the magnetic property of materials. So first of all, we need to define something which is called the magnetization. Now what is magnetization? Magnetization. Now magnetization is defined as, now whenever such magnetic materials or any material for that sense is placed in an external magnetic field, it could be a magnetic field due to a magnet, or it could be a magnetic field due to a solenoid, which is an electromagnet. For all those purposes, the magnetic dipoles present in the material media will get oriented along the direction of the field due to the torque acting, which we derived in our previous class as M cross B, and this is going to give rise to an orientation of the magnetic dipoles, and so we define a quantity called magnetization, which is defined as M, and this is equal to the magnetic dipole moment developed per unit volume. So if you have a volume d tau, limit d tau tending to 0, so this is defined as the magnetization of the material, net magnetic moment developed per unit volume, that is defined as the magnetization. So if we want to find the effect of magnetic properties on materials, then we need to first of all define the vector potential. From there we can calculate the corresponding magnetic field. So our objective of today's class would be first to evaluate the magnetic vector potential for a small volume and then integrate it over the whole of the volume. Let's say we have a magnetic material like this. This is a magnetic material. Any material can be magnetic. It could be paramagnetic, it could be diamagnetic, and there are certain materials which are even ferromagnetic. So we assume that we have a source over here whose volume is d tau prime, and it has certain magnetic moment m, small m, and with respect to some external arbitrary coordinate system, it has a coordinate r prime, and we want to find the field due to this magnetic moment at the point P, which is the field point at a distance curly r, which is actually at a distance r from the origin, arbitrary origin. The source point is r prime, such that our curly r is r minus r prime. Then the corresponding vector potential, according to our previous class, is given by m cross r by r cube into mu naught by 4 pi. Now, what is this m? This is the magnetic moment due to this small volume element d tau prime, which is basically equal to d cube r prime or dx prime, dy prime, dz prime. Okay. So what would be the vector potential at the point r? We can say, due to the whole of the magnetic material at the point P. Now we can replace this m from here as m d tau. So we can integrate it as mu naught by 4 pi, which is a constant, m cross r by r cube d tau prime integrated over the whole volume of the magnetic material. Now, how can we evaluate this m cross r by r cube? Now we know that r by r cube is nothing but grad prime of 1 by r, where grad prime is the gradient with respect to the source coordinate. That's why we didn't put a negative sign. Otherwise we could have put it like minus of grad of 1 by r. That gives us r by r cube. So we can write a of r as equal to mu naught by 4 pi m cross grad prime of 1 by r d tau prime. So one can write this integrated over the volume, over the whole of the volume. We can just write this as equal to curl of m by r as equal to curl of m by r plus m or grad prime of 1 by r cross m. We can just interchange this. We can write this as minus of grad prime of 1 by r cross m to be equal to curl of m by r minus curl of the whole of m by r. Or we can interchangeably, because we know that the cross product do not commute, we can write this interchanging m with, so m cross grad prime of 1 by r is equal to curl prime of m by r minus curl of m by r. So putting in the value of m over here, we can write the value of AR. Okay. So putting in the value of in AR, we get mu naught by 4 pi and m cross grad prime by r. In place of that, we are writing curl of m by r beta minus mu naught by 4 pi curl of as a whole m by r beta prime, the volume integral. So the expression for the vector potential becomes this, and we can say that this is fine. How about this? We can always, the first one remains the same and the second one can be written as, we know that curl of A some, okay, A or curl of any vector f, curl of f beta can be written as ds cross f. If this is a volume integral, then this is a surface integral, the surface which encloses that particular volume. That can be very easily proved from the vector calculus. How? Now you can just multiply or dot the left hand side, dotting LHS with a constant vector, let's say b which is constant. So this gives b dot curl of f beta is equal to divergence of f cross b beta prime. Okay, beta. Why? Because divergence of f cross b is equal to b dot curl of f minus f dot curl of b, but curl of b is a constant vector, so this goes to 0. So you can write, but divergence of a vector by Gauss's divergence theorem, one can write this to be equal to f cross b dot ds surface integral. Okay, now surface integral, closed surface which encloses the volume v, curly v. Now this is a dot b cross c. If we want to eliminate the constant vector b, then we can write this as a dot b cross c is equal to c dot a cross b. So this can be written as b dot ds cross f. So if b is an arbitrary vector, we can take out the b from the left hand side as well as the right hand side, and from here we can write very easily that curl of f d tau is equal to, if this is a volume integral, then ds cross f. So we can write curl of m by r, so we can write ar to be equal to mu naught by 4 pi curl of m by r d tau prime minus mu naught by 4 pi ds. This is a surface integral ds cross m by r. So we can write the vector potential as a, this is a volume integral and this is a surface integral. Just interchange the m by r cross n ds, okay, where n is the unit vector perpendicular to the surface. So we can write this as, so if we compare our normal expression of magnetic vector potential, which is given by mu naught by 4 pi for volume distribution, it is j d tau prime by r, and for surface current distribution, this is for volume current distribution where jr prime is the volume current density and the surface current density as k ds by r, where k is the surface current density and j is the volume current density. We remember that the volume current density is defined as the amount of the current passing through a normal area per unit area per second, and surface current density is the current change per unit lateral length. Okay, so we can say that for this particular case where we were considering a magnetic material and we were trying to calculate the magnetic vector potential for a particular magnetic substance at a certain field point P, we have the vector potential to give rise to two kind of current density. One is the volume current density in terms of magnetization and the other one is the surface current density. We call such current densities as bound current density. So bound currents, which is the first topic in your syllabus mentioned. So the bound current, volume current density, I would add a subscript B because of the bound. So I would call comparing these two equations J B to be equal to curl of M, which is given by the curling of the magnetization vector, and surface current density KB. If we compare these, then we get M cross N cap, where N cap is the normal to the. So we would further like to have a kind of physical significance of these two current density, and we will see that in our next class. Thank you.